The next thing that we need to talk about are ions. Ions are substances that have gained or lost electrons, and as a result have some electrical charge. So ions result because atoms gain or lose electrons, or entire compounds gain or lose electrons. When the total number of electrons is different from the total number of protons in the nuclei of atoms, we call the resulting substance an ion because it's electrically charged. There are two possibilities for how this charge works. Firstly, if there are fewer electrons than there are protons in the nucleus of an atom, then this means that electrons have been lost. Electrons, remember, are negatively charged, so if we lose some negative charges, then the positively charged protons win out. And the ion overall has a net positive charge. We call an ion with a net positive charge a cation. Cations, we can remember, are positively charged ions because there's a positive charge right in the middle of the word, T. Alternatively, if an atom gains electrons, it now has more total electrons, which are negatively charged, compared to protons, which are positively charged. Thus, electrons went out and the negative charges went out. So the ion has a net negative charge. We call any ion with a negative charge an anion, a negative ion. It turns out that many elements would actually prefer to exist as ions rather than as electrically neutral atoms, the way they're organized on the periodic table. Virtually all the sodium that we find, for instance, naturally occurring on Earth, doesn't exist as a sodium metal, a neutral element, but rather as an ion, specifically a cation of sodium that's lost one electron. And just like we can write isotope symbols for things that differ in numbers of neutrons, so too can we write ion symbols for things that differ in numbers of electrons. For this purpose, we'll always use our element's symbol, X, followed by a superscript that gives a number and a sign, positive or negative. For cations, we have a number with a positive sign. For anions, we write an element symbol, a superscript, that's a number, and a negative sign. This number is a charge magnitude, and it tells us how many positive charges or how many negative charges a particular element has. And more explicitly, tells us how many electrons have been lost or gained by an atom to make a particular ion. In these two shorthands, X is our element symbol. We'll have a number or numerical value for our charge, and we'll have either a positive sign or a negative sign, depending upon whether we have lost electrons and formed a cation, or gained electrons and formed an anion. To calculate the magnitude of the charge on an ion, whether it's a cation or an anion, we take the total number of protons that our element has in its nucleus, again, given from its atomic number on the periodic table, the number of protons, and subtract from that the number of electrons. Whenever there are more electrons than there are protons, we form anions, because that would indicate to us that an element has gained electrons. Whenever there are fewer electrons than there are protons, that indicates to us that our ion is positively charged and that we must have lost electrons. One final caveat about this: we only need to include a numerical value for a charge if the charge is different from 0 or 1. So do not include numerical values if the charge of an atom or ion is 0 or 1. Otherwise, we'll always include a numerical value for our charge. So let's do a few examples that illustrate how to apply these ideas. We're going to write ion symbols for, firstly, a potassium ion that's lost 1 electron. We need to know the element symbol for potassium. That's unlike potassium's name in that it's just K. The idea that potassium has lost 1 electron tells us that it must be a cation. So it's a cation because it has fewer electrons than it does protons. It's got 1 fewer electron. Compared to a neutral potassium atom. If this potassium has lost 1 electron, then its charge must have a positive sign, and because it's just lost 1 electron, there's just 1 positive charge associated with this potassium in net. We don't explicitly write the number 1 for a charge, so our ion symbol becomes simply K+. In this second example, a nitrogen ion has 10 total electrons. Nitrogen has the symbol N from the periodic table. But now we're told that it has 10 total electrons, not that it's lost some or gained some. So it's going to be our job to figure out which of those two nitrogen has done. Has it gained electrons or lost electrons to have a total of 10? To evaluate whether it's gained or lost, we need to look at the number of protons that nitrogen has, which is unchanging no matter what we do to electrons. The number of protons in nitrogen is 7, because nitrogen is atomic number 7. Thus, we can calculate its charge from the formula we wrote in the box up above. Its charge must be the number of protons minus the number of electrons. 7 minus 10 is -3. And the ion symbol for nitrogen with 10 electrons then, we know that nitrogen will be an anion. It's going to have a negative sign. And the number or numerical magnitude of charge is 3. We write that as 3 negatives. There are 3 negatives associated with this nitrogen anion, and 3 minus. As an aside, you could also write N-3, so the superscript on this right-hand side really doesn't matter in terms of order. Typically, I'll write the magnitude of the charge first, followed by the sign positive or negative second. So let's recap what we've talked about. We've discussed ions and isotopes. Ions vary in numbers of electrons. Isotopes vary in numbers of neutrons. Elements are always identified exclusively by the numbers of protons they contain. That number doesn't change, lest we change the identity of an element itself. Elements can change their numbers of neutrons. Variations of atoms that have differing numbers of neutrons are called isotopes, and we see a change in isotope reflected in the total mass of the individual atom or average mass of the element. Elements can simultaneously or separately change their number of electrons. We call a result an ion because these things are charged. The gain of electrons means that an atom has gained negative charge and has become negative. We call a negatively charged ion an anion. And similarly, the loss of electrons means the loss of negative charge, so that an atom becomes positive. We call such an ion that's positively charged a cation. Now what we're going to do to summarize things is determine the numbers of protons, neutrons, and electrons in substances that may be charged. So we have two isotope and ion variations. One is silver 109 plus. The second is Br79 minus. We need to be able to interpret from these symbols what the numbers and signs mean. Any superscript to the left-hand side indicates a total mass or mass number. Any superscript to the right-hand side indicates a charge. The easiest quantity to determine is the number of protons that each one of these atoms, ions, isotopes contains. Silver, Ag, is atomic number 47. Therefore, it must have 47 protons in its nucleus, regardless of how many neutrons or electrons it contains. To determine the number of neutrons, we'll take advantage of what we know about a mass number. A mass number is the number of protons plus the number of neutrons. If we know the number of protons, then we can deduce the number of neutrons by subtracting from our mass number, 109, the number of protons, 47. 109 minus 47 is 62 neutrons. Lastly, the number of electrons can be determined based on what we know about charge. The charge on an ion is the number of protons minus the number of electrons. Therefore, because we know the charge is +1 implicitly from this superscript on the right-hand side, then 1 is equal to the number of protons, 47, minus the number of electrons, an unknown value. Or rearranging this to solve for the number of electrons means that we must have 46. But an easier way to think about the number of electrons is just to consider what a positive charge means. A positive charge, and a single one at that without any number in front, means that there must be one electron lost. All cations have lost electrons. How many electrons has this cation of silver lost? It's lost 1. That means it has 1 fewer electron than protons. If it had 47 protons, that must mean it has 46 electrons now. We can apply those same principles to the bromine anion down below. Bromine is atomic number 35, so it's got 35 protons. The number of neutrons is 79, the mass number, minus 35, which is 44. And the negative charge, without a numerical value, indicates that this is an anion that has gained 1 electron. 1 electron compared to the number of protons it has. It has 35 protons. If it gained 1 electron compared to that, it must now have 36 electrons. Again, the worksheet that I've posted for you on your course Moodle page has a whole host of example problems for you to work on with the solutions attached, so you can practice counting numbers of protons, neutrons, electrons, and determining the charge and mass number of isotopes and ions. Before we go on to our last slide, we're going to work together to fill out this periodic table worksheet. You have a copy of the same worksheet available to you on your Moodle page for the class. And when you open that, you should see one that's not filled out just like this. We're going to work our way through this together so that you can follow along and fill out your own version. We have some terminology that we need to learn and become familiar with as relates to the periodic table and the organization of the elements themselves. The periodic table is very intentionally laid out to have rhyme and reason to the way in which elements are grouped together and ordered. Firstly, elements exist in individual rows. 1, 2, 3, 4, 5, 6, 7 rows. where this lanthanide series and actinide series are just extensions of rows 6 and 7 respectively. We call those individual rows on the periodic table periods. Secondly, elements are arranged in columns. There are 18 total columns whose numbers are given at the tops of each respective column in turn from 1 on the left to 18 on the right. We call these columns groups, or sometimes we'll see them referred to as families. Elements that share a group share similar properties, behaviors, and tendencies towards chemical reactions. And because of that, we give certain groups special names. The ones that you should become familiar with are the names for the first and second groups, this and this, the collective term for groups 3 through 12 across the middle, and the last two groups on the right-hand side, 17 and 18. Group 1, or Group 1A, are called the alkali metals. And Group 2, or 2A, are called the alkaline earth metals. As you might imagine, these things that are to the left of an imaginary bold line running down the right middle portion of this periodic table represent metals. Elements to the left of that bold line are metals. And because chemists are creative, we call anything that's to the right of this bold line over here nonmetals, because they're not metals. Elements that touch the bold line directly, not diagonally, so things like boron, aluminum, and silicon, but not carbon, are called semimetals or metalloids. So the left-hand side of this periodic table is populated by metals. The right-hand side is populated by nonmetals. This transition from metals to nonmetals is populated by what we call collectively in groups 3 through 12 transition metals. Again, because chemists are creative in how they name things. For the nonmetals, groups 17 and 18 represent important features of the table. Group 17, fluorine, chlorine, bromine, iodine, are collectively referred to as halogens, H-A-L-O-G-E-N-S. And group 18 is sort of like the holy grail for elements on the periodic table. Those are noble gases. All elements on the periodic table that aren't noble gases tend to want to become more like a noble gas. And they do so through chemical reactions. It turns out that there are 7 elements that we find naturally occurring on Earth as diatomic molecules. Remember, molecules are collections of more than one type of atom. Diatomic means that we must have collections of 2 atoms in a single chemical substance. These 7 naturally occurring diatomic molecules include H2. This chemical formula means that 2 atoms of hydrogen are uniquely bound into one single new chemical substance. Similarly, we'll have N2, O2, F2, Cl2, Br2, and I2. And aside from hydrogen, which is its own little black sheep over here, the remaining 6 of 7 elements that exist as diatomic molecules trace out a 7 on the periodic table. So this is a nice convenient means by which to help us remember these 7 naturally occurring diatomic molecules. Finally, what we'll find through the rest of this section of the course is that elements, like the rest of the universe, are lazy. And chemical reactions are going to happen primarily through the interaction of electrons and the gain or loss thereof. Elements will try to gain and lose electrons to become most similar to a nearby noble gas. And they'll do so in the least energetic way possible, or they'll maximize their laziness. Nonmetals, things that are over here on the right-hand side of the periodic table, tend to want to gain electrons to become like noble gases. So nonmetals gain electrons, generally speaking. Metals, we'll say, are losers. Metals are losers. Specifically, they're losers of electrons. Why is this? Take, for example, an element like fluorine. Fluorine is not a noble gas because it's not part of group 18. Fluorine has 9 electrons. But its nearby neighbor, the noble gas neon, has 10. Fluorine would really like to have 10 electrons, just like neon does, because when you can match your number of electrons to a noble gas, you feel like you are, at least outwardly, a noble gas yourself. To become something that has 10 electrons, fluorine would need to make an anion with a -1 charge. It would need to gain 1 electron. And the same is true for chlorine and for bromine and for iodine. Each one of these elements would have to gain 1 electron to make it become isoelectronic, or have the same number of electrons as a noble gas that's immediately adjacent to its right. Therefore, what we're going to do is place a big -1 at the top of this halogens group. Halogens tend to form anions with a -1 charge. Meanwhile, oxygen would like to be like neon too. To do so, oxygen with 8 electrons would have to gain 2 electrons from somewhere. Sulfur and selenium would have to do the same. We're going to put a big -2 at the top of this group that contains oxygen, sulfur, and selenium. Nitrogen has 7 electrons. If it could gain 3, it would be isoelectronic, or have the same number of electrons as neon. And so we're going to place a big -3 at the top of this column that contains nitrogen and phosphorus and arsenic. These substances tend to form anions with -3 charges. But notice that by the time we get to carbon, carbon with 6 electrons could gain 4 to feel like neon, but it could also lose 4. So let's come back to carbon in a little bit and skip our way over to the left-hand side of the periodic table and look at lithium, atomic number 3. Lithium has 3 electrons. It would really like to feel like a noble gas, and it's not one right now. But neon is all the way over here. To have as many electrons as neon, our little lithium would have to find 7 new electrons to gain. That's a lot of work to do. 7 electrons is a whole lot. And lithium is lazy. Lithium doesn't want to have to go to all the work of finding 7 electrons, when lithium could just lose electrons instead. Notice that helium, atomic number 2, comes right before lithium on the periodic table. If lithium were to lose one of its electrons, it would have 2 left, just like helium does. And it sounds a whole lot easier to lose 1 electron than it does to gain 7. So lithium will lose an electron. Sodium, potassium, rubidium, cesium all do the same. So we're going to put a big +1 up at the top of this group. The alkali metals tend to form cations with +1 charges. And similarly, the alkaline earth metals will also lose electrons, but they'll lose 2. A substance like magnesium, atomic number 12, could lose 2 of its electrons to have 10, the same number that neon does, which comes before it. We're going to put a big +2 at the top of this alkaline earth metals group. We're going to omit the transition metals for now because they're crazy and do weird things. So we'll come to group number 13 next, the group with boron, aluminum, gallium. These elements tend to form +3 cations, as something like aluminum, atomic number 13, would have to lose 1, 2, 3 electrons to become like neon. And so once again, we end up with this group containing carbon and silicon. If carbon were to lose electrons to become like helium, that comes before it, carbon would have to lose 4. If carbon were to gain electrons to become like neon, that comes after it, carbon would have to gain 4. There's no real benefit or trade-off to losing versus gaining 4 electrons. So for the most part, carbon just stays put like it is and tends not to form ions all that often. So we're just not going to bother writing a charge at the top of this group here. What that means for us then is that based on an element's position on the periodic table, we can predict how many electrons that element is likely to gain or lose through the course of a chemical reaction. Again, chemical reactions are largely predicated on the drive of elements to become like a noble gas, like those elements in group 18 of the periodic table. One way that elements can do this is through forming substances called ionic compounds, which we'll talk about in the next chapter. We can predict from the periodic table what ion an element is likely to form given its position in a particular group. For example, if you look at the periodic table we just filled out, sodium is in group 1A, the alkali metals. We just put a big +1 at the top of that group 1A column. We expect sodium to form cations with a +1 charge, Na+. Calcium is in group 2A, the alkaline earth metals. We expect calcium to form a cation with a 2+ charge. Bromine is in the halogens group, upon which we placed a big -1. We expect bromine to form a substance Br-. Oxygen is in a group that has a big 2- at the top. We expect oxygen atoms to gain 2 electrons and form O2- anions. And lastly, aluminum we expect to form 3+ cations. We're going to use these as lead-ins to help identify how bonds between ions form and how to write down chemical formulas for those resulting ionic compounds, new chemical substances that arise due to the loss and gain of electrons.